Okay, we're doing three friction problems. First one is just on flat surface, where we're pulling this crate or this box that's sitting on the surface with a force of 100 newtons. We're going to give a coefficient of friction mu that's equal to 0.2. And the mass of this thing being 10 kilograms, if we draw in the forces that exist on that box, we've got our gravitational force that's equal to mg. And in this case, we've got a normal force that's equal in magnitude to mg that we'll use to calculate our friction. So anytime we're talking about an object moving, if it's going to accelerate, the acceleration is always caused by the net force. So if I'm pushing on a cart with 5 newtons of force and you push back on the other side with 3 newtons of force, it accelerates as if there's 2 newtons of force. Okay? If I push with 100 and you push with 98, it accelerates as if there's 2 newtons of force. So the net force, I don't care if it's 100 minus 98, okay, or 5 minus 3, if the net force is 2, it accelerates with an acceleration based on that net force of 2. So when we look at the box and decide if it's going to accelerate, we need to look at the net force on the box. We'll write that as F net. Sometimes in some texts, you'll see, especially the book that we use, the Survey text, you'll see summation of the forces written instead of F net. It's the same thing. So I'm going to write net force. In this case, if this thing's going to accelerate and move forward, then this force of the pull, there has to be some left over when we look at the forces that are opposing it. In other words, this has to win by something if it's going to accelerate. So there has to be a net force that's not 0. And in other words, if I'm going to get this to accelerate, then Fp minus the frictional force in the opposite direction, it has to still be some type of a value with some sort of magnitude. It can't cancel and become 0. And obviously my frictional force isn't going to be bigger than my pull. Okay, so in this case, what we do is we just substitute what we need in here. If it's going to accelerate, if this mass is going to accelerate, this force, it's going to accelerate with an amount that's equal in magnitude to the pull minus the friction. So we just substitute ma in here. That's the mass and its acceleration. The net force determines what really happens. Okay, so what really happens is this mass accelerates with some value for acceleration that's equal to this push minus this frictional force. Now the equation we're using for the frictional force, because we've been told it's going to accelerate, and even if we weren't told, we could calculate this based on a small mu, is going to be the normal force. Sometimes you'll see just a capital N written there, but the normal force times the coefficient of friction, the 0.2. And in this case, since we're on a flat horizontal surface, the normal force up from the surface is equal to the gravitational force downward. So we can write in our, let's go ahead and substitute our number for our mass. We've got 10 kilograms here times our acceleration is equal to the amount of my pull, 100 newtons, minus my normal force is mass times acceleration due to gravity, my 10 newtons, times my 9.8 meters per second squared. That's my normal force, and then I'm multiplying by mu. Mu is determined experimentally between any two surfaces. So in this case, I have two surfaces that are rubbing together, and the slipperiness, stickiness, whatever you want to refer to it, okay, for this one has a value of 0.2. We do that calculation, we end up with 10A equals 100 newtons minus 19.6 newtons. Okay, and we're left with 10A is equal to the result of that was at 80.4 newtons, divide by 10 on both sides, and we get an acceleration of about 8 meters per second squared for that block. Okay, so this is the block just on a flat surface here. If we look at second scenario, say if you needed to see that a little bit longer, go back and hit pause. Second scenario, we're going to take this same block. Let's talk about dragging it with that same force. Okay, up the hill, 10 kilograms. Now let's say our hill has a theta of 20 degrees. Now I'm not going to calculate the final answer on this, but we'll walk you through the steps of doing the exact same thing here. If this thing's going to accelerate up the ramp, we need to look at the net force on the object, and in terms of the direction that it might accelerate. So we've got the pull upward, and that's going to be our main force that if it accelerates upward, it has to win, essentially. So again, I'm going to put my the force of my pull, and now I have to think, well, what's opposing that pull? I've got two things. Number one, I've got still a frictional force this way. Okay, that's subtracting some of the force away to give us a net force that's smaller than the pull. And I've also got gravity working on this thing. Now the gravitational force is not directly down the ramp. The gravitational force is always straight downward. So we draw that in here, labeled mg. So how much of that force acts down the ramp opposing my pull? Well, again, we're looking at components. So I'm going to break this down into its vertical and what I would call x and y components in this case. So it's as if I've turned my Cartesian coordinate system so that my x-axis is here and my y-axis falls here. Okay, so I'm looking at the amount of the acceleration or the amount of the force here. I'll label that Fg in my x direction, and I can draw that force in here. It's the force of gravity just in the x direction. And that force of gravity in the x direction down here would be, plug in our theta of 20 degrees, would equal mg. I'll write that there. Mg cosine theta. So when I'm looking at my net force equation, I've got F net, I've got the pull up the ramp. Okay, so my F net's going to equal this pull, but I'm taking out my frictional force, and I'm taking out the amount of the gravitational force that works down the ramp, Fgx, that we can label as mg sine 20 degrees. Okay, so there's the component of my force down the ramp, and I wrote cosine here. Sorry about that. Sine theta in that case. Okay, so we need to substitute everything in here that we're wanting to look at. First of all, let's look at our frictional force. Our frictional force, let's rewrite this. F net is equal to Fp, that's my 100 newtons, minus my frictional force. Frictional force is normal force times mu. Okay, and then I've got my component of the gravitational force down the ramp. Well, what's my normal force in this case? Now we're looking at our other component of the gravitational force, the y component here that's equal to mg cosine 20, or mg cosine of theta here. That's my y component of the gravitational force. That's how hard the gravitational force pulls the box against the surface, and because of Newton's third law, is also how hard the surface pushes back against the box. So that's going to be the normal force that determines my frictional force. It's not all of the weight anymore. Over here my normal force was equal to the total weight down. Now my normal force is equal just a component of that weight, only the y component, the portion of that weight that works against the ramp. And as I tilt the ramp steeper and steeper, of course, it pushes less and less upward on the object, and we get a greater force down the ramp, okay, as that angle becomes bigger. So my normal force here, F net, is going to be my Fp minus my normal force. My normal force becomes mg cosine 20 degrees. Don't forget to substitute in still little mu times 0.2. And then I'm subtracting out mg sine theta. Okay, so this would be the equation for my net force on this object, and now I would substitute in the mass of the block times its acceleration. I'm putting in my 100 newtons here. I'm going to leave out some units here so I can save some space. Plugged in my mass, 10. My acceleration due to gravity, 9.8. Cosine 20, I don't know that value, so I'm going to keep writing cosine 20 times 0.2. Minus 10, 9.8. And sine 20. It's probably not still on the screen over there, but you get the picture. Okay, so this would be the third case, or second case, where we're dealing with a gravitational force and a pull that's not in the x and y planes of a normal Cartesian coordinate system. Third scenario that you might see then, again, we're just dealing with one block, not entire systems. So let's go back to this first scenario where we have flat ground. But instead, here's my 10 kilogram box. I'm going to pull it with a force of 100 newtons again. But I'm going to do it at an angle. So there's my 100 newtons, and let's say I'm doing that at an angle of, I don't know, 25 degrees for theta. Okay, and how does that change my equation? Okay, so again, I'm looking for F net. If I want to know how much this box is accelerating, let's say U is still 0.2, okay, just like we had before. So I'm looking for how much this box is accelerating. My net force is again going to be equal to how much I pull it with. Well, I need to look at the pull that's in the direction of the motion. So I'm looking for this F, P, in the X direction. Okay, that's going to be the maximum amount of pull in that direction. Because my rope is pulling to the right, but it's also pulling some upward. So I'm not going to have the full 100 newtons, the full effect of the 100 newtons pulling in the direction of the motion, of the proposed motion. Okay, and you can see, obviously, if theta got steeper, that there would be even less and less of a component pulling it forward, more component pulling it upward until we were completely vertical, and the pull wouldn't have any effect on the horizontal motion at all. So this is where we're starting from. We're still taking out, if it's going to move that way, we still have a frictional force that's this way. And our numbers are large enough here that we can see that it is going to accelerate. One of the things you might find over here is if we were calculating an acceleration value, what if we came up with a negative number for my acceleration? Well, what that would mean is that these forces I've calculated down the ramp this way are greater than the force that's being pulled up. In other words, it would want to accelerate down the ramp based on this scenario. We don't have that situation here. We'll still get a positive acceleration, but if we did, we would then want to look and say, oh, well, this pull's not great enough to hold it up the ramp. Okay, maybe it accelerates down, and in which case we have to look and say, okay, if it's maybe going to accelerate down, let's flip the friction to the other side. Okay, but going back to this problem, our values are large enough that we're not going to have that scenario. So we still have our frictional force here that we're taking out, and our frictional force is still equal to normal force times mu. Okay, so we're pulling this way, we have a pull back this way. And if we want to look at the value of that normal force, okay, it's no longer equal to, sometimes we label it N, like I said, mg, you label it Fn if you want. Okay, my normal force here now is not as strong as it was before because my force upward also has a component in the vertical direction. And that gives the box a little bit of lift, so it's not pushing against the surface as much as it would before. So we call this our FPY, the amount of the pull force, the 100 newtons in the Y direction. And that we could draw out here if we wanted to. It's equal to the F times sine 25. And this one being equal to F cosine 25. So those are the ones we're going to plug in down here. If I want to know my net force, the mass that's moving times its acceleration, I've got to know the pull that's forward. That's my F cosine 25 minus my frictional force, that's F sine 25. And don't forget to plug in your mu. Okay. Big force minus the backwards force gives us our acceleration, or our net force. We'll plug in our mass here. This is our force of 100. Here's our force of 100 again, and we can solve for acceleration. So hopefully that helps you work through some of the simpler examples. Once we start putting two blocks together, tied with pulleys, tied with strings and things, again, remember, make sure you're breaking down to your free body diagrams if you're not familiar with doing that. Okay, look at the other videos that you have online, and those should help you with that as well. Thanks very much.